All right, man. Let's get this going.
All right, I'm ready.
Go ahead.
All right. So today we're going to be covering cellular respiration, the topic we're going to be doing. Kyle Richardson and John Matamora are going to be presenting every segment to you. And basically what cellular respiration is how we make energy, how our body converts glucose all the way to energy. The basic molecules for glucose, the equation is going to be 6 carbon, 12 hydrogen, 6 oxygen. It's 1 mole of glucose plus 6 moles of oxygen. After everything's done, the whole process is you're gonna end up with energy. It's gonna be 6 moles of carbon dioxide, 6 moles of water, and then plus your energy, which is gonna be dispersed into how your body uses the heat, and also the amount of ATP your body can effectively use.
Right, which is what
It's
the
about
main
30.
issue, which is the main thing we're trying to get out of this whole thing.
Yep.
Is energy. For daily activities, from sleeping to reading to actual strenuous activities like what? Working out, anything, right?
Any kind of physical activity you want to do.
Without
It's how your
ATP,
body-
there's no life, so.
Exactly, your body produces and uses ATP.
All right, so as Kyle was saying, the first step is what, Kyle?
The first step of respiration process is going to be glycolysis. So you're going to take the carbon backbone of a glucose molecule, it's 6 carbons there. You're going to use 2 ATP to break it down in what's called a P-gal. Breaks it down to 3 carbon molecules. During the ATP breakdown, they're both going to add a phosphate molecule to each P-gal. These 2 P-gals are broken down even further. It's going to, each breakdown creates pyruvic acid, which it loses the phosphate, becomes just pyruvic acid there. Each P-gal, when it's broken down, creates 2 ATP for each. And then all the NAD pluses get a hydrogen molecule attached to them, making them NADHs. So at the very end, you've got 2 for each and then plus NADH.
Okay, so we're looking at a total gain of what, 4?
Total gain of 4. It's going to be a total gain of 4 ATP during this process. You've already used 2 to break down the initial molecule,
so
which gets you 2. So one of the disadvantages of this process is it only makes 2 ATP. It's kind of minimal advantage. But an advantage of it is,
what is an advantage?
it requires no oxygen. It's anaerobic. It doesn't need any oxygen to do. And this all takes place in the cytoplasm of the cell. And then it all moves on further into different parts of the mitochondria.
All right, awesome. All right, Kyle, what's the next step?
All right, next step in the process after glycolysis is going to be the conversion of the pyruvic acids to acetyl-CoAs that we have left over from the previous step.
Now, is there anything different here?
This step does require oxygen.
Oh, okay.
This is the first step that requires oxygen in the process. It all takes place inside the matrix, which is the innermost part of the mitochondria.
Okay.
Now, during the process, the pyruvate acid is oxidized. Now, these 3 carbon chains then drop down to 2 carbon chains, making your acetyl-CoAs. During this process, though, one of these carbons is going to be expelled as CO2 as a byproduct, a waste byproduct. Now, also in this process, your NADH or NAD pluses, get hydrogen molecules attached to them again, making more NADH for later use. Now, the total outcome of this process, you're going to end up with 2 acetyl-CoAs, 2 carbon dioxides that are being expelled, and then 2 more NADH molecules. All right, John, so what's after the conversion, what's the next step?
All right, man, so the next step is called the Krebs cycle. During the Krebs cycle, we take acetyl-CoA taken from the conversion step and combine with oxaloacetic acid, I know it's hard to pronounce there, which then combines to form citric acid. This whole process is citric acid breaking down back into oxaloacetic acid to combine again with acetyl-CoA to redo the cycle again. All this is happening still in the matrix, and it does require oxygen as well. Now, as you can see here, we're getting hydrolyzed with NAD plus turning into NADH, which is gaining an electron. Basically, all these electron carriers are going to play an important role in the electron transport chain. We're expelling CO2 through the respiration of, just breathing in and out. And ADP gains a phosphate to turn into ATP. FAD turns into FADH2. Now, in summary, since we're doing this cycle twice from each pyruvate or pyruvic acid, we have to account for basically twice as many molecules for each kind. So we end up with 6 NADHs, 2 ATPs, 2 FADH2s, and 2 CO2s as byproducts.
All right, John, so what's this next step here?
All right, man, so the last step is the electron transport chain, what everybody's been waiting for, right? So we're still in the mitochondria, and we're still requiring oxygen. with this, we're gonna blow up this image right here. We're gonna get the inner membrane and the outer membrane. This is the inside of the matrix, and this is it called the inner membrane space. We're gonna blow this up even further, and we're gonna zoom in over here. And these are channels, protein channels, except number 2, we'll get back to that in a second, that allow the movement of hydrogen ions into the inner membrane space. So to do so, we need to start the electron transport chain, which is marked in green. How that starts, we can start off in channel 1 with NADH. It donates an electron, opening this channel, allowing hydrogen ions to diffuse through the inner membrane space. Now that electron is going to get carried over to Q, which is going to get carried over to channel 3, which is going to get carried over to cytochrome C, channel 4. Get back to this in a second. Channel 2, I just want to talk about real quick. FADH2 releases an electron to Q to continue the electron transport chain. With these products, these reductions here, NAD plus and FAD, we can reuse again in the Krebs cycle all over again. So we're keeping the cycle going, the electron chain going strong. So with the last electron acceptor is oxygen. So with oxygen, it attaches this to free-flowing hydrogen ions to form water, which is a byproduct. Or we get just forget about it. It's not important. With all these hydrogen molecules flowing into the inner membrane space, we have an accumulation now of hydrogen ions. With this, we're creating a concentration gradient, which is greater inside the inner membrane space than in the matrix. So now these molecules, they want to flow to the path of least resistance. To do so, they can only travel through this enzyme, which is called ATP synthase. Through ATP synthase, these hydrogen ions spin a turbine as they go through. And in doing so, they rotate this, like I said, this turbine, which is smashing these ADPs and phosphates together, or combining them, to form ATP. The rest of these hydrogen ions just freely flow into the matrix. So now the total gain really is from the 10 NADHs that we started off with. So 10 times 3, we get 3 of those, that's 30. And we start with 1 FADH, I believe 2, right? Yes, 2. And we multiply that because we get 2 ATPs, so the total is 34 ATPs. Let's say an advantage of this is that it is a very high, crazy amount of ATP, considering these other stages only produced just at the most 2 ATPs each, it looks like, at the most. So a disadvantage is that it requires oxygen. Without oxygen, you can't have this process going, which will not produce any more energy.
All right, Kyle, looks like we presented cellular respiration pretty good. Wouldn't you say? Wouldn't you say so? Okay, what are we looking at, man?
All right,
Summary.
so we'll do a basic summary of everything, all the steps we've kind of gone through. First step is glycolysis. We start that process with some glucose. At the end of that whole step, we're going to have yielding 2 ATP, 2 pyruvate, and 2 NADHs. Next step is going to be the conversions process. Those 2 pyruvate are going to turn into 2 acetyl coenzyme A's. We're also going to yield 2 carbon dioxides and also 2 more NADHs to get pushed down to the electronic transport chain. Next step is that Krebs cycle. That cycle takes the 2 acetyl coenzyme A's, mix it with the oxaloacetic acid to get some citric acid. At the end of that whole cycle that rotates twice, you end up with 6 NADHs, 2 more ATP, 2 FADH2s, and then a couple more carbon dioxides that get expelled. Then at the very end, the electron transport chain, we take the 10 NADHs that we've collected through the whole series, the 2 FADH2s from the Krebs cycle, and after that whole chain is done, we ended up yielding 34 ATP.
Okay.
Now, when we talk about the ATP, overall, we're going to net 38 ATP. However, we do gain in total 40 ATP because we have 4 ATP from the glycolysis.
Correct.
Then you lose the 2 ATP for doing the actual work, netting you just the 2. 0 from the conversion process, 2 more from the Krebs cycle, and then 34 is the big one from the electronic transport chain, giving you 38 ATP. And that is the entire process of cellular respiration. Hopefully that made sense to everybody. John and I had a good time doing this, and hopefully y'all enjoy it.